Excellencies, ladies and gentlemen, dear friends, scientists, many of you I know, I have worked together, and it's great to be here back at WMO. I should first of all thank Petri Talas and Pavel Kabot for the very kind invitation to give this inaugural lecture. This is a great honor for me, and I try really to look a little bit forward into the future. What is there in for us? What is there in for us scientists to contribute to some of the biggest challenges of humankind that lie ahead of us? And in order for us to really take the same view, I start with this picture, which you all very well know. It's the photograph of our home, including all humankind except one person, the person who shot that photograph from Apollo 8 on 24th of December 1968. Half a year before man set foot on the surface that you see below. I not only like this picture for the beauty of our planet, but also for the message it gives us that in space there can be habitable locations and extremely uninhabitable locations. You see the moon's surface, I would not want to live there. You see the Earth, our home, where we can live. I want to focus on 4 points here in the next 25 to 30 minutes. First, look back at the assessments. I think a success story, as rightly was pointed out by the Secretary General of WMO, a success story that has taught us many lessons, a success story of hundreds, if not thousands, of individuals who have contributed to the knowledge that we dispose of today regarding the state of our planet and its possible future. I then want to focus on models, because these are tools to actually provide us with numbers and insights that are quantified, on which we can take informed decisions. The third point is an important topic that I believe is really at the heart of our capability to gauge the risks of climate change. And I want to say a few words about that, about the confusion that I sense in the wider public about these processes and a possible way out of that. The last point, I think, is also central to our future. I sense emerging discussions on geoengineering, and I want to share a few thoughts, a few personal thoughts about that important topic with you tonight. Just let me transport you back a couple of decades when scientists were in front of this curve, these observations, fantastic high precision measurements of carbon dioxide from Mauna Loa. And just imagine yourself for a minute that you as a scientist look at this curve. Would you be concerned? Would you see something special here apart from the seasonal cycle and the slow trend? Well, a few scientists at that time in 1978 were concerned. We're very privileged that these colleagues have been concerned. It's also, for me, a home run to actually remember two colleagues from my institute at the University of Bern who have published in 1978 a paper predicting the future atmospheric carbon dioxide levels. Uli Siegenthaler and Hans Oeschger, both physicists interested in the carbon cycle and the questions, used a simplified model, a box model, to predict carbon dioxide concentrations in the year 2000. They said in their paper in 1978, which I find quite remarkable, a maximum permissible atmospheric CO2 level might be found which should not be exceeded if the atmospheric radiation balance is not to be disturbed in a dangerous way. Published in Science magazine, 1978. Now let's look at what happened since the publication of that paper. Nature has unfolded together with humans fully in the Anthropocene. CO2 has been increasing. And look at the precision of the prediction made in 1978 for the concentration of carbon dioxide in the year 2000. This is one of many examples to illustrate that science actually had it right for many decades. Science delivered dependable and robust results on which decisions could have been taken already at the beginning of the 80s. Now we know much more. We know that this increase of carbon dioxide concentration, the most important greenhouse gas after water vapor, is not just a coincidence or part of natural variability. We have actually brought the atmospheric composition of greenhouse gases in the atmosphere totally out of balance. This is illustrated by this time series that shows you a reconstruction of carbon dioxide concentration over the past 800,000 years based on ice core measurements that we did at the University of Bern. You see the natural variability there. You see the ups and downs of carbon dioxide that go hand in hand with the cycles of the large ice ages. Just to remind you, 20,000 years before today, which is still at the far right of this curve, Geneva was under an ice sheet of about 800 meters depth. So ice was from the Rhone Glacier, from the valley down into the Rhone Valley to France, but also up through the Mittelland of Switzerland. That was just 20,000 years ago. Today, the concentration is really high, 414 ppm, 35% higher than ever in the history of the past 800,000 years. Obviously, as we all know, caused by the emission of fossil fuel combustion products, oil, gas, and coal, and land use change. So man has really changed the Earth's balance, both chemically and physically, and that is depicted in this picture. So in that time in the 70s, which was quite a remarkable decade, we knew about the carbon cycle, but we knew also about the physical system. In 1975, my former postdoc advisor, Wally Broker, passed away a few months ago. He wrote a landmark paper, Climate Change, Are We on the Brink of a Pronounced Global Warming, in 1975. And only a couple of years later, a group of scientists published the first climate assessment. Precisely 40 years ago, this paper, this document came out. It was commissioned by the National Academy of Science, chaired by Jules Charny, and one of the members of that distinct group was actually Bert Bolin. If you go and look up what they said in their document, they said the consensus of these studies has been that increasing carbon dioxide will lead to a warmer Earth with a different distribution of climate regimes. 40 years ago, everything was here. The assessment was here, the notion of consensus was here, the knowledge about the carbon cycle was here, the knowledge about the physical response of the Earth system was here, and you all know this report even quantified climate sensitivity at around 3 degrees Celsius for a doubling of carbon dioxide concentration. Quite remarkable. Anyways, I think the decade of the 70s and 80s prepared the ground for a remarkable foundation by two organizations of the United Nations, by the WMO and UNEP. I'm referring to the foundation of the Intergovernmental Panel on Climate Change. And that panel has, and I just show here a few examples, published since 1990 5 comprehensive reports and is now in the process of preparing the 6th comprehensive report, which is supplemented, as in earlier cycles, with special report targeted on specific issues, the last one on the 1.5 degree world. It's a remarkable organization. It's a fantastic organization that brings together scientists from all over the world to find a consensus on some of the hardest scientific questions. Many people have criticized consensus finding, in particular those who question climate change. But in my personal view, consensus is the only way how you can provide a robust and transparent snapshot of the knowledge. Nobody assumes that our knowledge will be eternal or complete. And therefore, it's actually a message in itself that you have a series of assessment. And that series obviously needs to continue with the evolution of the scientific knowledge. Out of the last report, a few statements came out, proposed by the scientists and approved in consensus by all countries. Warming of the climate system is unequivocal. Human influence on the climate system is clear. Continued emissions of greenhouse gases will cause further warming, and limiting climate change would require substantial and sustained reductions of greenhouse gas emissions. In essence, all things could have been said already in 1979, if we think about it. But these statements, at least, are now in consensus by all countries. And as such, they are the foundation of important agreements. I'm just highlighting one figure out of our last report in the 5th assessment report, which cost a lot of sweat and negotiation skills to bring this curve through in our summary for policymakers. It shows you the linear relationship between the emissions accumulated since the pre-industrial times and the warming expected in the 21st century. This linear relationship is the basis for many political negotiations. For example, what it takes to bring us not above 2 degrees warming relative to pre-industrial. So this is a highly policy-relevant picture and graph, and just stands as an example of the many policy-relevant results that come out of these assessments. Let me take a first conclusion here on the topic of assessments. The scientific assessments were clearly the foundation of the Framework Convention on Climate Change. Remember, that convention was designed in 1992. The first assessment report of IPCC appeared 2 years earlier in preparation of that topic, just one of 3 that the Earth Summit in Rio has tackled. The other 2, biodiversity and desertification, 2 other more conventions that have been born out of this remarkable summit. And the Paris Agreement. The Paris Agreement wouldn't be there without the scientific foundation brought to the policy makers through the mechanism of the Intergovernmental Panel on Climate Change. And with that, I think WMO and all people involved who have dedicated their time can be very proud of that achievement. I also note that the pace of the assessments and the political and public expectations have increased considerably. While in 1990 a handful of scientists could actually carry out the assessment, the first assessment reports, and I remember they were under stress too, but the stress level has just increased and the pace is very quick now, with 3 special reports in the pipeline and a comprehensive report of each of the 3 working groups plus a synthesis report. And I think this itself constitutes a growing burden on the scientists and the scientific community and everybody involved in preparing and publishing these reports. And I think the risks associated with that growing burden must be managed appropriately. Let me come to the second point. which is, I think, closer to many of the people that are here in the room. It's about modeling. Models provide us with the numbers for our diagrams in IPCC. They actually quantify the state of the Earth in a physical sense and biogeochemical sense, but also allow us to look into the future. And one of the most important instruments to do that is the World Climate Research Program with many of the activities, and I just pick out one. Doesn't mean that I leave the others apart, but I just pick one here that provided the projections for the many IPCC reports. The Coupled Modeling Intercomparison Project, now in its 6th phase, a very organized effort, bottom up from the scientific community with the help of WMO and WCRP. But you see, quite a complex beast by now, as you can see in this diagram or disk. I won't go into that, but CMIP now consists of 23 sub-MIPS, Model Intercomparison Project, all of which provide very interesting material for the scientists, but also provide a lot of data, numerical data that has to be analyzed. And of course, there is not an end to that. People start already talking about CMIP 7, CMIP 8, and here you start wondering, can this burden be carried by the scientific community and by the institutions who provide the computational power and the intellectual power for that? Just as an example, there is still a lot of work ahead. Here is a picture, a map showing the discrepancy of sea surface temperature relative to observed. And I like to show that picture as well because it illustrates that without observations, we would not be able to evaluate models. So observations are at the heart of any of our activities trying to understand the climate system and map out its future. There are some important areas that show biases or discrepancies. Upwelling regions in the subtropics, think about El Nino. If we can't model these systems correctly, how can we trust in short-term predictions of, for example, El Nino events, which are an important phenomena for many areas in the tropical region? Or think of the monsoon systems, a life-giving natural phenomenon of variability in the climate system. If we can't simulate that and assess its response to the warming, some countries are in real trouble. But there are other areas, the western boundary currents, which are themselves a location of potential instabilities in the climate system. Big discrepancies there, just measured by the deviation in sea surface temperature. And finally, the Southern Ocean, also in itself an extremely crucial area and region for two reasons. One, the uptake of carbon dioxide, and second, its vicinity to the Antarctic ice shield and the various streams and outlets around Antarctica. That leads me to the second conclusion. Climate change scenario calculations have become near operational. It's a big machinery, but they are still carried out by research centers. And you can rightly ask the question, is that the task of a research institution to carry out these calculations? Comprehensive climate models must reach the next level of realism. We've seen that. I've just shown you a sea surface temperature as an indication of deviations, but I could have shown you many other important quantities in the climate system that require improvement, but also enlargement in terms of the included processes. Think about the ice sheets, think about ice streams, surface cover on the land, but also in the higher strata, in the higher atmosphere processes that, as I will mention later, will be important to understand. Seamless climate prediction is within reach. We have heard it, and I think model development behooves us well to actually provide, at the end of the day, robust and dependable climate predictions. They are absolutely essential for countries, for regions, to plan their resources in case of climate development and change. The third point here concerns something that you can read a lot in the media, and it's always at the top of the attention when a new paper comes out. It's about the tipping points or instabilities, or sometimes they're called surprises in the climate system. Already in the third assessment report of the IPCC, which was published in 2001, we had a little box on surprises in the climate system. That was many years ago, and today we have a prolific literature on these issues. What are they? Again, we start out with observations, and you can see already looking at the time axis that these observations are scarce. They are short. We don't really have a full appreciation of the natural variability of important quantities like the red curve, the meridional overturning circulation in the Atlantic Ocean, or the strength of the Gulf Stream, that's the top blue curve. If you look at these short time series, you may be tempted to draw lines. Had you drawn the line around 2011, you would have talked about a decreasing trend. You would have quantified that trend and compared it to then available model simulations. Had you started your observations a little bit earlier because your first proposal was declined, fortunately it wasn't, but had it been declined, you would have identified an increasing trend in the meridional overturning circulation. And if you now make the attempt of putting a straight line to these data, I don't really know how robust that small negative trend is. The point I want to get across here is that we absolutely and direly need observations together with the best possible models that we have to look and gauge at the future of this important indicator of ocean circulation. Because models tell us that there are bifurcations in the nonlinear system. I show here a simulation that goes out to the year 2600. It's carried out at NCAR. You see here extreme climate scenarios. By the way, we are on the road of the red scenario right now, but you also see that we are at the very left of the graph, and it's still in our hand to determine whether we will stay on the red curve that shows an extreme warming in the future centuries, or whether we manage to limit the warming as foreseen by the Paris Agreement. But if you now look at the meridional overturning circulation in this state-of-the-art climate model, a coupled climate model developed to the best of the ability of the scientific community, you see there is a bifurcation here in the system whereby the system reacts linearly in a way and recovers that important circulation for small warmings, but moves to a different equilibrium state for larger warming. Likewise, another system is certainly of concern, and that is the cryosphere, particularly the ice sheets. They are on a stringent diet, as you can see. They are losing mass. They have been losing mass over the last few decades, as you can see here. Fantastic measurements that become available through our capacity to observe Earth from space, not just through the lens of a Hasselblad camera, but through sensors that actually quantify the changes. Here the mass of the Greenland ice sheet that loses mass at a rate of 400 gigatons per year. For those who can't relate 400 gigatons per year, like myself, I translate that into sea level rise, spreading that annual contribution to the entire ocean surface, and you get at about 1.2 millimeters per year. This sounds small, but it's about 30% of the current observed increase in sea level. Likewise, Antarctica is on a diet. You see here the surface mass balance in blue. That's not concerning, but the mass balance overall, which is the red curve, which includes the mass loss through ice streams around Antarctica. And you can see here that ice sheet is also under dietary stress, 130 gigatons per year currently, as the most recent publications indicate. Now, as we have shown a couple of years ago, if you take the very long perspective of such a melting that is induced through man's emissions of carbon dioxide into the atmosphere, we're talking over the range of about 5 to 10,000 years of possible sea level increase by about 50 meters. That assumes that you lose large parts of the Greenland and Antarctic ice sheets, as is indicated in these little icons there. That scenario is not unavoidable. Let's be clear about that. But it's a quantitative estimate of what could happen if tipping points are crossed or if warming is not checked. Conclusion 3. Just a few conclusions. Our understanding of tipping points in the Earth system is rapidly growing, a lot of publications, but also observational capacity is increasing, but it's still crucial to continue these time series to monitor these critical points in the Earth system. I also believe that this is a highly policy-relevant topic that needs further attention, and because of the many media reports on tipping points and the many voices that you can hear in this orchestra, it's actually very difficult to come up with robust knowledge on that topic. And therefore, I personally believe an authoritative assessment should be very timely on this topic. And in fact, I stick my neck out here. I personally would very much welcome an IPCC special report in AIR7 on tipping points in the Earth system. This is a topic that is now mature for assessment, and I think an assessment is a healthy process where consensus is being built in the scientific community, and a few robust statements should come out of such a report. Let me now come to the last point here, something that already confronted us in the 5th assessment report. At the time in 2011, 2012, it became clear that geoengineering is a topic of great public and scientific interest. And therefore the request came that IPCC not took a position, but certainly thought hard about how to reflect geoengineering in its 5th assessment report. Well, geoengineering can actually be divided in 2 classes of technologies or methodologies. On the top, you see the carbon dioxide removal with a few examples here. This is a picture from the 5th assessment report, deep down in some of the chapters. And in the lower half, you see the solar radiation management with a few examples there as well. And I want to focus particularly on the solar radiation management because that technology or methodology is the one that is discussed most in the public fora, and it's also often portrayed as the cheapest fix in the climate system to keep temperatures down. Now, there are some very interesting studies. It started already at AR5 with one of the MIPs, GeoMIP, Geoengineering Modeling Intercomparison Project, but it has now become much more sophisticated with simulations that have become available in the past few years. You see here one of the examples where 4 injection points are defined in the low latitudes in the stratosphere. They're indicated by black dots, and you see here the sulfur concentration, sulfur being that ingredient injected into the higher levels of the atmosphere to reflect sunlight and therefore influence the Earth's radiation balance to such an extent that the warming would be reduced. Not much is seen here in 2020 to 2039, but if you continue these simulations, you see that in fact a well-chosen source strength of sulfur injection into the lower stratosphere actually manages not only to keep down the global mean temperature, as you see in the top of the right panels, but also some temperature measures that have a dynamical implication. For example, the interhemispheric temperature gradient can be kept down artificially by this injection of sulfur into the stratosphere, or the equator to pole temperature gradient, as you all know, that is important to characterize the storm activity in both hemispheres. So seemingly, at face value, a very interesting experiment that holds some promise. But now look at the sulfur concentration in the end of that simulation to actually hold down the temperature by about 5 degrees from what it would be under RCP 8.5. And you see that we've basically contaminated with sulfur dioxide the stratosphere in a substantial manner. A whole layer of this substance is sitting up there. Of course, it has to be replenished because the stratosphere actually loses that sulfur in the hydrological cycle that also affects the stratosphere and washes that substance out. So continuous supplementation of this component has to be maintained. What I want to focus your attention on is this diagram here. Before you saw the sulfur concentration. Here you see the temperature differences that are imposed on the stratosphere. And as you know, the stratosphere is the home of many complex chemical reactions. Chemical reactions need activation energy. Activation energy is a function of temperature. If you change the temperature, there is a potential to change the chemistry in the stratosphere. That is why it's so important to include chemical reactions, as this model did actually, in your calculations of possible impacts of such experiments on the Earth system, not only on the atmosphere, but on the entire Earth system. So here we are changing permanently the temperature increase in the stratosphere by 10 degrees. At the same time, we're decreasing the temperature in the higher stratosphere, as you see in the blue color. So we are imposing a temperature gradient, an artificial temperature gradient in the stratosphere with little known consequences. You also see this is a continuous commitment. This diagram shows the injection rate, how many million tons of sulfur you have to deposit in the stratosphere every year. And that depends quite linearly on your climate target. If you want to hold down the temperature by 1 degree, so for every degree Celsius, you have to inject 10 million tons of sulfur every year. This is a large burden on humankind. I don't know how much money will be left to actually reduce carbon dioxide emissions that are the origin of your commitment here in this diagram. But there is another issue with sulfur injection and artificial cooling of our planet to offset the warming caused by carbon dioxide increase, and this is depicted here, already shown in the 5th assessment report. It concerns the so-called termination problem. It's very simple concept. If you do geoengineering and hold the temperature down below 2 degrees or even below 1.5 degrees warming relative to pre-industrial, there is no motivation to decrease carbon dioxide concentrations and to decrease carbon dioxide emissions. So these emissions will actually continue to increase. It's like a spring that you load. And if future generations tell you that maybe this injection has some side effects that were unintended and undesired, we stop with this injection. You basically let go one end of that spring, and that leads, as you can see in that lower curve, to a sudden warming that is actually factors faster than the warming that we see today. That is the termination problem that exists in temperature, but also in the hydrological cycle, as is shown in this right diagram. The hydrological cycle also changes and also exhibits a termination problem that starts here. So this increasing and growing commitment that comes with geoengineering, in particular the solar radiation management, bears risks that need to be quantified in order to be communicated correctly and robustly, and also require assessment to understand what the consequences of such decisions might be. Let me therefore conclude here for the fourth topic and then wrap up with a few concluding remarks. Geoengineering, in particular SRM, bears risks that are global, unknown, and unquantified. I believe personally that stratosphere resolving physical chemical models are absolutely essential to inform us about what is going on and what will be going on in the stratosphere in terms of the chemical reactions, the concentrations, the consequences to ozone, etc., just to name one. Geoengineering may constitute dangerous anthropogenic interference. It actually will be dangerous anthropogenic interference. And as we all know from Article 2 of the Framework Convention on Climate Change, that actually should be prevented. So let me close here this first lecture, hopefully still in time. Robust climate assessments need more and stable resources. Extensive scenario computations must be institutionalized. Climate models must reach the next level of realism to enable seamless climate prediction and the prediction of resource availability to the regions and the countries. I think about El Nino, I think about monsoons, I think about the hydrological cycle in Southern Europe, for example, the droughts in America, the rainforest in South America. All regions need this seamless climate prediction, and they need it in a robust and correct manner. Knowledge on tipping points is important, I believe, because that has an implication for our decisions, and here I wish that some consensus emerges in this rather disharmonic melody that you can listen to in the media about this topic. And finally, geoengineering in itself constitutes or may constitute a dangerous anthropogenic interference with the climate system, and this is on purpose given in quotes. That's from Article 2 of the Framework Convention. And with that, I'd like to close, and I'd like to thank you for your attention coming here and listening to my thoughts. Thank you very much.